Start with a problem, sort of a quiz problem, because, well, it is a quiz problem. Okay. And this is basically what we did in class last time. So we have a closed jar of water. It's at 80 degrees Fahrenheit above room temperature at 10 o'clock a.m. It sits there. The room doesn't change temperature. It's 20 degrees above room temperature at 2 p.m. We want to find an exponential model for the temperature, capital T, versus the time, lowercase t, little t. So temperature will be big T, time will be little t. We use the model then to predict the temperature at 12 o'clock noon. So go ahead and begin. See how far you can get. Take the initial information and do the appropriate thing with it. Okay, now hopefully you've at least got a good start, but let's see how this would go. First, you want to represent the information graph, and that'll be represented as 2 points on a graph. Now, if you haven't done that, stop and see if you can do it. Okay, everybody should have either done this or attempted to do it. So I'm going to go ahead and sketch a graph here. Capital T for temperature, little t for time. Times in hours, temperature in Fahrenheit degrees. We have 2 points on this graph. We have when time is 10 o'clock a.m. Just put 10 somewhere. We don't really care where the origin is. Put a 10 here for 10 o'clock. The temperature is 80 degrees Fahrenheit. I'll put 80 Fahrenheit here. And where those two lines intersect is a point that represents the fact that when the time is 10 a.m., the temperature is 80 Fahrenheit. Okay. Say 10 a.m. Okay. Now, we also have 2 p.m. when the temperature is 20 Fahrenheit. Well, let's do the temperature first. If 80 is here, then the temperature is 0 on the t-axis. So halfway between 80 and 0 is 40, and halfway between 40 and 0 is 20. So 20 would go about here. That is, this horizontal line would represent 20 Fahrenheit degrees. And that's at 2 p.m. So let's just go ahead and put 2 p.m. here. Now, working with AM and PM can be a little bit of a pain. So I would actually change this to say 24-hour time. Starting at midnight, 10 a.m. is hour 10. 12 o'clock is hour 12, and 2 p.m. is hour 14. And that's military time. And now our hours will be measured in military time. In any case, where the 2 p.m. or 14 o'clock military time meets the 20 Fahrenheit line, we have another point indicating that at this time, the temperature is this. At 14 o'clock, temperature is 20 Fahrenheit. Now we want to do an exponential model for temperature versus time. So I would say the second step is it's an exponential shape through the points. Now, we work really on sketching an exponential shape. First on sketching an increasing exponential shape, like in a box, it's going to look something like this. Okay. If it's a decreasing exponential shape, well, it's going to be like this thing flipped over. It'll come down like so and do this. So here to here, we would have an exponential shape that maybe does this sort of thing. It continues on approaching zero. And we should understand that about the exponential function. It's going to go on up here through, it's probably going to intersect the t-axis somewhere up here. We're not too interested in that. And we're not expecting this shape to be a really good approximation of the exponential. But it still represents something that looks like it might be an exponential curve. If we look at it a little more closely, and we will in a while, we're probably going to find out that it's flawed. And I'll find my own flaws and you can find yours. These two steps give you concrete picture. There's a C in the word sketch. To give you a concrete picture of the situation and of the function. Now you can find the exponential model by turning a crank and just doing what we do. If you do this, you're going to understand everything a whole lot better. You're going to have a bigger picture and it'll be easier to remember, even though there are more things. It's easy to remember the picture if you've got a lot of things related to each other, if you understand those relationships. So if you haven't taken the third step, the next step, go ahead and do that. Okay, well, hopefully you've had a chance to pause and do the third step if necessary. You don't know what third step I'm going to put down here, but you can make up your own third step. Hopefully it'll be one of the steps that I take before I'm done. Well, third, choose an exponential function form. Could be t equals a times b to the little t. Could be big T equals a times e to the kx. Could be big T equals a times 2 to the kx. And there are other possibilities. The 8 times 2 to the kx has some advantages. It's pretty easy to get a grasp on the half-life if you're using this function. If you're going to do calculus with it, this is the function you want. This is the easiest function to do calculus with. If you want to analyze the model without using logarithms, you're going to choose this model, okay? Either of these involves logarithms, and I'm actually going to choose one of those two models. So I'm going to make that choice just by circling, and I'll do the A equal to the KX model. So the fourth step, plug the information into the model. Okay, well, we have a big T and an X. Now, I used AB to the T, and then I started using AE to the KX and 2A times 2 to the KX. And let's be consistent. Let's use T for the independent variable. Because we're talking about time, it makes sense to use T. Okay, so we have big T equals 80 and little t equals 10. So using this model, we're going to have 80 equals A times E to the K times 10. And of course, I'll write that as 10K because we usually write the number first. We just plugged in 10 for T here. So you got E to the K times 10, which is E to the 10K. And then T equals 20. Big T, temperature is 20, with little t, time is 14. So 20 equals A E to the 14 T. Now notice that we have two equations here. Those two equations each have two variables, A and K. P here, where I should have written a K. Gonna have to keep an eye on me this morning, okay? So we have these two simultaneous equations. I'm going to solve these equations. I'm going to start the solution over here. Probably won't have time or room to complete it. And I'm going to put the AE to the 10K on the left and the 80 right, the first equation. And the AE to the 14K equals 20 here. Now, there are a couple of ways we can begin to solve this set of equations. So if you haven't done so, give it some thought. See if you can take a couple of steps towards solution. Okay, there are a couple of ways you can solve this. You could solve the first equation for A, you would get 80 divided by e to the 10K. Then you plug it in here, and you have this A would become 80 divided by e to the 10K. Then e to the 14K divided by e to the 10K is e to the 4K. And there are other steps we can take, and that's a perfectly good way to solve the problem. I'm going to say in this case, I find it a little shorter to just divide the first equation by the second, because if you do, the a's will divide out. I'll say divide the second equation by the first, just because that'll avoid some negative numbers. Okay, so this is a first equation here. This is a second equation. When we divide the second by the first, we have A E to the 14K equals, well, sorry, A e to the 14K, left-hand side of the second equation, divided by A e to the 10K. That's going to equal the right-hand side of the second equation divided by the right-hand side of the first. And if we divide this out, the A divided by A just gives us 1. E to the 14K divided by E to the 10K is E to the 4K. Make sure you thoroughly review the rules for logarithms if you don't know why E to the 14K divided by E to the 10K is E to the 4K. 20 divided by 80 is 1/4. So now we have an equation that we can solve for K. How do we solve the equation for K? Well, this is an exponential equation and its basic form. So let's come back up here. We have E to the 4K equals 1/4. Now, you should take a minute to digest these steps and see if you can solve this equation. Okay, good. Hopefully you've paused and done that if you haven't already done it. Now, this equation is the fourth on B to the A equals C is the form I usually use. There are other forms, but it's an exponential form. Something raised to a power equals some number. Here we have some number raised to a power equals some number. B equal to E, A equal to 4K, and C equal to 1/4. What's the equivalent form? What form is equivalent to B to the A equals C? What form do we use in solving exponential equations? Take a minute, see if you can pull that out of memory if you haven't already, and see if you can solve the equation. Okay. Well, the equivalent form is log base B of C equals A. Now, if we use this form with these values of A, B, and C, we get log base E of 1/4 equals 4K. Now, log base E of 1/4 is a natural log of 1/4. Say natural log of 1/4 equals 4K. Natural log of 1/4 is something you can do with your calculator. You have natural log K, usually labeled ln, and then apply that to 1/4. Okay. So I'm thinking that's going to be about the reciprocal of 1.3. Okay, taking a wild guess, which would mean that the natural log of 1/4 would be about wait a minute. Natural log of 4 is between 1 and 2, closer to 2.7 than it is to 7.2, quite a bit closer. Natural log of 4 ought to be 1.2. Natural log of 1/4 ought to be then negative 1.2. Now that's a very approximate result. Okay, it's approximately this, and that's based on an estimate I did in my head. Your calculator will give you a much more accurate result. I think it's going to be pretty close to 1.2, between 1.1 and 1.3. But let your calculator tell you whether I know what I'm doing or not, okay? So then we solve for K. Divide both sides by 4, we get K equals negative 0.3. Okay, so now we've got K. How do we get A? We have to know A in order to get the model. So see if you can get A if you haven't already. Okay, hopefully you've paused and gotten the model for A. Just take the first equation. First equation is A e to the 10K equals 80. Okay, well, that gives us AE to the 10 times 0.3, and it's negative 0.3 equals 80. Well, we're going to have to column up here to finish this. Got plenty of room. So we have AE to the negative third equals 80. So A equals 80 over E to the negative third. Now I'm getting, which seems like kind of a ridiculous result, but it isn't all that ridiculous when you think about it. Okay, E to the negative 3 is ballpark 16. Now you can put this into your calculator. You don't even have to evaluate e to the negative 3. You can do 80 divided by e to the negative 3. Have an e button on your calculator. Wouldn't hurt. But yeah, the decimal equivalent e to the negative 3, which would be around 0.06 or something like that, isn't going to have a whole lot of meaning to it. When you divide this, you're essentially going to multiply 16 by 80. And that's going to give you about 1,280. Okay, it'll be 1,280 degrees Fahrenheit. Now, turns out the half-life is about 2 hours, so you have 5 half-lives. 5 half-lives, you're going to decrease the temperature by a factor of 256. Well, you can check it out. You can see if this model works. Okay, so our model on 5 half-lives would only be 32 into 1280. Still, something's bothering me, but follow the steps and get what you get. If I'm inaccurate here, don't be too surprised. Okay, our model. Remember, our model is T equals A e to the KT. Becomes T equals A, which is 1280 e to the negative 0.3 T. That might work out. Okay, well, now we check. For t equals 10, we get big T equals 1280 e negative 0.3 times 10 equals 1280 e to the negative 3. And e to the negative 3 is 16. 16 times 8 is 28. Okay. Wait a minute. Can't be right. It's 144. Okay, I do have a wrong number here, but this thing works out. This correction. Apparently my mental arithmetic is off today. That approximately equals 80. We would also check for t equals 14. Now 14 times negative 0.3 is negative 4.2. So you can multiply e to the negative 4.2 by 1440, and you should get something pretty close to 20. Again, remember that this number I got here could be off by 10%, okay? Which should cause some real errors over here. So you want to take my estimates with a grain of salt. You want to do this and get your own results. All right. Now I'm going to see whether my curve is really exponential. I want to estimate, based on the curve, I want to estimate the temperature at 12 o'clock. Okay. So we estimate temperature big T at time little t equals 12. Okay, well, we know little t equals 12. How do you represent little t equals 12 on the graph? See if you can do that. Okay, hopefully you've paused and done that. Then 12 is halfway between 10 and 14. It's a value of t. So right here, halfway between these two vertical lines, I'm going to put the vertical line for 12. And then I'm going to make a horizontal line here through the point where the vertical line intersects the graph. The value of big T on this line is going to be my estimate of the temperature at t equals 12. Time little t equals 12. Now I'm going to make a couple of auxiliary lines here. Halfway between 80 and 0 is 40. And there's a halfway point. So I would say big T equals 40 on a line that's pretty close to this one. Actually, that line is a little high. T equals 40 should be a little lower. So let's make that line just a little bit lower. Now, if T equals 20 here and T equals 40 here, my 20-degree Fahrenheit is here. And let's make sure we know which line is which. So there's 20 and there's 40. This line's a little bit closer to 40 than it is to 20. So I'm going to estimate, make your own estimate. What do you think the Y value or the big T value is for this line that I just drew? It's between 20 and 40, a little closer to 40. Make your own estimate. Okay, hopefully you've paused and done that. I'm going to say this is T equals 32. Now remember, this estimate is based on the curve that I drew, which is almost certainly not totally accurate. Okay. So this is saying when little t is 12, big T is 32. Now, I'm not going to make a mental estimate of that. I can do e to the negative 3.6. I'm probably not going to be very accurate. You can see if our model tells us that T equals about 32, temperature T, when time little t is 12. So plug that into your model. Tell me how we did. Okay, now I'm dying with curiosity. So I'm just going to quickly plug this into a model on my computer. Okay, I just used Wolfram Alpha, which is I can type, but it's like punching buttons on calculators, puts you in the wrong physical position and everything else, and it's quicker to type. And I checked out several things. I plugged in 1440 times e to the negative 3. I got something closer to 70 than 80. That's not surprising because remember, my estimate of this number was a little bit off. Okay. And actually, I can get an estimate of the natural log of 1/4. I estimated 1.2. We can see how close I came. If we can get up here. And Wolfram is telling me that that's, gee, I was way off with that. It's closer to 1.4 than it is to 1.2. Okay. So when I did this step, my estimate wasn't very good at all. I should be better than that at estimating natural logs. Okay, it's not that hard. So this model was somewhat off, which made this model somewhat off. Your model should be more accurate. If you plug in 10 into your model, you should get something pretty close to 80 if you used a calculator. It also told me that I should have gotten t equals 39 here instead of 32, which means that my exponential curve wasn't particularly good. Okay. It's a little too abrupt. And it did pretty well agree with the 20 degrees Fahrenheit. If I plug in t equals 14, I get something very close to 20, 21 point something. You can check your model in that way.